So what you saw, where is it? Over here? Thank you. What you saw is, and if you held it up to the light, oh, did it break? So what you're seeing here is the reason that memory is called core, and you've seen core dumped, yes? Okay, so you'll undoubtedly see it a lot more in your careers. And I explained what it is that it means, core dumped. And that in the old days, there was little enough memory that nobody's going to come in, so just close the door even it's locked. It means that so memory was so small that when a program poked the dragon, the entirety of its RAM would be, of its core would be written to disk, making a core dump. And using that, you could use a debugger to perform a post-mortem on the crash and discover why and where the crash occurred. So why is it called core? Well, those little tiny black spots are actually donuts, ferrite cores. They are ferrite iron which can be magnetized. And as you saw, they are really, really, really tiny. And they are oriented looking at the board like this. They were oriented edge on a diagonal. And there are a number of wires. Think of this as X and Y. Think of this as X. Think of this as Y. And think of an extra special tiny one as doing a couple of jobs. One would be to energize, put the core in a state where it could be magnetized. Once that signal was taken away, it would stay in the value that you set. And also, it could be used to read the magnetic orientation of the core. So in order to read a byte, 8 bits, it would, in sequence, you can address the individual core, which is 1 bit, and go to the next one, and the next one, and the next one, and read out the magnetic polarity of these little iron beads. And that's how core got its name, is these are cores. Another interesting thing about what you just looked at is it was made by hand. Okay? So somebody sewed these by hand. Little teeny tiny fingers and magnifying glasses, and it's crazy, isn't it? So the memory board that you're looking at is circa 70s. How much RAM was on that one board? Any guess? Yeah, about as much RAM on that memory on that card as a small email. So, not much. Okay. So I've got some new knowledge for today. Before we go into review and before we go, actually we should start with review, yes? So not questions about the project, which I assume everyone has done. It is due tonight, correct? So what? Was it due last night or tonight? I think it's tonight. The comp org assignment was due last night. Right. Okay. So you can just resubmit over the top of your previous submission if you've made one. Nick, is there a problem? You have a look of consternation.
There's no problem.
Okay. Right. See, it's a liberal arts school, so you get to hear all sorts of interesting words. When I was a kid, we didn't have video games. So what did I do for entertainment? I read the dictionary a lot. There's a lot of words in the dictionary. Most of them are medical. Did you know that most words in the dictionary, a good dictionary, are medical words? Because those bozos need to think that they're, really smart, so they just invent words for everything. Like left, they have a different word for left. They have a different word for middle, different word for right. So, okay. So, doctors, can't live with them, won't live long without them. Okay, so the new knowledge that I want to talk about today is bit bashing, bit twiddling. And the reason we want to talk about it in this class is so that in a future class, I can assume you already know it. So this is for me, not for you. And believe me, it will be very good for me. You? I don't know. Okay? So what is bit twiddling? Bit bashing. We work with bits. We just saw bits. We just looked at them. Right? So you've been working with bits, but you've been working with them at a higher level of density, a higher level of abstraction. So you've been working with integers. Integers are collections of bits. You've been working with strings, it's a collection of bits, but at a higher level. So integer, how many bits in an integer? How many bits in an integer? That's a good point. It depends. That's a wonderful answer. How many bits in an integer in the typical program that we write in class?
16.
No, the proposal was 16. It's 32. Okay. And how many bits are there in a float? All of them? What? Also 32. How many bits do you think there are in an integer called a long?
64.
Yeah, 64. Yeah, and how many bits do you think there are in a double? Also 64. How many bits do you think there are in a pointer on a 64-bit machine?
7.
What is the color of George Washington's white horse? Who's buried in Grant's tomb? These are the questions my father, if I asked an obvious question to my father, that's what he would tell me. So what color is George Washington's white horse? White, yes, that's right. So on a 64-bit machine, how big are pointers? Okay, the definition of it being a 64-bit machine is that addresses or pointers are 64 bits. Yeah,
So I tried to, a few days ago, write a factorial program.
Uh-huh.
And I used a long.
Uh-huh.
And then I put in like 120.
Yep.
And I think,
You just got a 0. If it overflowed, you might not get a 0. So I wonder, did you work for other values that were smaller?
Yeah, it worked perfectly for me. Because 120 factorial is
really, really big.
really big.
Yeah.
So
But 64 bits is really, really, really big.
Is it 120 factorial?
I don't know offhand. But to give you a sense of how big 64 bits are, yeah.
Is it 6.68 times 10 to the 190?
Oh, yeah, it's a lot less than that, 64 bits, I think.
So,
well, put in 2 to the 64th and tell us what that is. So you said 190, 10 to the 190 something?
Yeah, that's 1 to the 19.
Okay, so 64 bits is something to 10 times 10 to the 19.
Yes.
Okay.
1.844.
All right. So good. So we have we know that 120 factorial is much bigger.
So how would you represent that? If you have to write, like I know that people like to write big number
Right.
libraries.
You represent numbers that big by writing a big number library.
So it just doesn't come with C.
No, it doesn't, but you can get it, you can download it. A big number library would implement the changes to math operations like multiplication and addition so that it would work on multiple 64-bit values. So, for instance, it would calculate a carry. You know what carries are because 9 plus 8 is 7 with a carry of 1. It's the same thing in binary. So it would look for a carry out of the first 64 bits, factor that into the second 64 bits, and continue so on. You can have an arbitrary precision math library. But let me get back to my story here. So a 2 to the 64th is so big that if you strung pixels together, so look at your screen and a dot on your screen. If you strung pixels together side by side and started in the middle of the sun, you could get Saturn in 2 to the 64th pixels. It's a really big number.
What
Okay.
about 198?
I don't know, but it would be science fiction, right? Yeah.
So maybe it's a little off topic, but you mentioned,
I never go off topic in this course. Okay, go ahead. Just for you.
oh, okay.
Yeah.
So you mentioned pixels, and
Uh-huh.
I'm just curious, like like I see like a little dot, then you look at like all the TVs and whatnot, and they talk about pixels, but you have to have the 3 different lights in it, so they're small, but how small? Like
Mm-hmm.
I don't know. I
It
guess.
varies.
Yeah, it varies from device to device. For example, a Retina display on a Mac or a Retina display on a Mac will be about 272 dots per inch, pixels per inch. So that's how big they are. 1 over 272 per inch. Okay. Now, another thing that you referred to is how deep are they? And that's an interesting question. That's what I was supposed to talk to the Huffington Post about, but I guess they lost interest. These things happen. So a pixel is on your computers, if you're not looking at a GIF, that's a little bit different. But by the time a GIF image hits your monitor, it's the way I'm about to tell you, and all JPEG images, what you're looking at there, everything on a modern monitor that's not special. I'll get into the special ones. They are organized like this. There is a red, a green, and a blue, except if you're on Windows, in which case there is a blue, a green, and a red, because so each of these are a primary color. What is the primary colors that you may have learned? What are the primary colors that you may have learned when you were little kids and you finger painted? Anybody? Yeah.
Red, yellow, blue.
Red, yellow, and blue. Okay. We could, you know what? I'm feeling like we're going to spend an entire lecture on this because I really love this subject. It's what I did to make my billions. So, so you had red, yellow, and blue. Yeah. Okay. But your monitor has red, green, and blue. Yet you can still make colors out of both of them. Anybody have a, yeah?
It's the primary colors of light, right?
Primary colors of light.
When you can combine or diverge them in a certain way, like to make a certain color for light.
Well, if you're referring to a prism, then what happened to Roy G. Biv? red, orange, yellow, green, blue, indigo, violet. So that's light. In fact, as everybody should know, light is a continuous spectrum, not only of the visible wavelengths, such as these, but radio and microwaves and gamma rays and X-rays. It's all light. So my question again is, which one of these is right? Which one of these is right? Yeah.
I'm retracting my hand. Actually.
Okay. Yeah.
Well,
No. Okay.
Pigment mixing is different than mixing light.
I think what you're referring to is correct, and that would be called additive light. Additive mixing is different from subtractive mixing. So those would be better terms. Additive is if the device is shining light at you, whereas subtractive is if you are looking at something, a surface, and light is bouncing off of it to enter your eyes, like a poster on the wall or a newspaper. So they actually are the yin and yang of each other in most respects. So which one of these is right? Yeah, all of them. Yeah. Now, for human beings, it turns out that we have in our eyes the most common photoreceptor that we have in our eyes detects intensity of light, and it doesn't see color at all. In other words, it's black and white television, black and white camera. So most of our visual acuity is in black and white. Then there are three types of color receivers. And one of them peaks its sensitivity in the reddish. The other peaks its sensitivity in the greenish. And the other peaks its sensitivity in the bluish. Right? So that's why it was natural to make monitors that were red, green, and blue, because it corresponds essentially to the color receptors in our eyes. Now, notice that red, green, and blue add up to 3. There are 3 of them. You've heard dogs only see red, maybe? So how many color receptors do you think they have? Just 1. It happens to peak in the reds. So it's not true to see that dogs see everything in red. If all you have are reds, how would you know what red is? Right? So if I were to hold up the handle here, a dog would just say, that's bright. But if I hold up the pen cap, dog would say, that's dark. Okay, so it's not actually colors that they're seeing, but intensities that are peaking in the reds. Do you know any animals that have 2 color receptors? Anybody? Okay, they do exist. New World monkeys. So not apes, not Old World monkeys like African monkeys, but New World monkeys, monkeys native to North and South America, have 2 color receptors. And what about 3? You know any animals that have 3? Huh? Us, right. What color is George Washington's white horse? Okay, and who else? All the other great apes. They have 3. So is 3 the most you can have? Yeah. What?
Third picture's more, right?
Yeah. So 3 is not the most you can have, yes?
On Google, it says the aggressive mantis shrimp has 12 types of chromosomes.
The aggressive mantis shrimp. The ones that are chill, they have fewer. Right. So the duck has 5. You know how beautiful and like emeralds and blues, and their breasts sort of just shimmer in the light. You know, the duck. Yeah. Well, who knows? We can't really imagine what it is that they're seeing. You know, for all we know, ducks recognize each other by having their URL on their. You know, every duck has a URL on it. You know, we don't know.
I mean, we
We can make a mathematical model.
yeah,
We can conceptually understand it.
and we could probably make a camera that can see more. We have cameras.
I suppose, yes, we do. We do.
And just,
But we have, in order to, so that's a good point. We do have multispectral cameras. We do have cameras that see in wavelengths we can't. However,
it has
we
be
have to
simplified.
process. It has to be simplified in some way in order for humans to process it. So who knows what it is that ducks see in each other, right? The mantis shrimp has 12. No, excuse me. The angry mantis shrimps. The aggressive ones. Stay away from them. We don't go near them. Yeah. You try to eat one of those, forget about it. Okay. So monitors have red, green, and blue. Now the question you might ask now is how many reds, how many greens, how many blues? Oh, well, let me make a final comment about primary colors. Any set of primary colors, any set of colors makes our primaries. Any set of colors are primary colors. What differs is, given those primaries, what range of colors can you represent? So for instance, if I only have 2 colors, there exists some planar representation of all colors. I don't want to go into it now, it's kind of complicated. But imagine on that planar map of all colors, we have 2 of them. Then the gamut, or the word gamut, refers to the total range of color that any set of primaries can represent. The gamut are all the colors on the line between them. And when we have 3, it's all of the colors on or inside the triangle. Right? How many colors are that? Well, this is kind of like floating point. So a better question would be, how many different colors can humans distinguish? Okay? And it's more than what I'm about to say, but not way, way more. And I don't know the exact. But of course, it's been measured. Anything you can do to write a paper on, you go ahead and measure and write a paper. So what I want to know is, what is the depth of red, green, and blue? Are you enjoying this? Are you learning something? Okay, it's how your cameras work and things like that. Okay, so this is, guess what? Bits. And that's how we get back to, yeah?
We can compute the bits, 256. Because usually, I think the span is 256 distinct
Levels.
Yeah.
Levels of brightness, right? So this is 8 bits, and this is 8 bits, and this is 8 bits. Or 256 values, 256 values, and 256 values. So this is how many colors that your typical monitor, television screen, etc., can represent or show you, technically. So putting 8 and 8 and 8 together is 24. So 2 to the 24th is a little bit more than 16 million. Okay, so your monitors are capable of a little more than 16 million different colors. It turns out in the practical world, they're capable of fewer because inaccuracies in the monitors, maybe they mush together a bit or two. So a high-end monitor will come closer, in fact, meet the all 16 million. Okay. Now here's an interesting thing. Would you be surprised to know I have yet another pet peeve? Would that surprise you? Okay, you go to the doctor and you get an x-ray, you get a CAT scan, you get who knows what, but your life depends upon it. So you're going to pay probably a few $1,000s for an expert to, quote, read the results. The bozo may be looking at it on his or her phone. All right? And if they are looking at it on a monitor, phones often show fewer colors than this. If you're looking at it on a monitor, it's an uncalibrated consumer monitor. So I just said monitors mush together bits. So they're making life and death decisions about you based upon a monitor that somebody bought at Best Buy. Okay? And that makes me uncomfortable. What they should be looking at the very least, is a calibrated monitor. And even better yet, there exist monitors that are 10 bits each and monitors that are 12 bits each. So when Game of Thrones, the people who created Game of Thrones are probably looking at monitors up here. And so what they saw when they were preparing the Game of Thrones episode 3 probably looked nothing like what we saw on our televisions. Right? So these were the duck feathers, and we saw comic books. Right? And I would really prefer if my doctor was, reading, my radiologist was reading one of these, but these cost more, so they don't buy them. All right, so 36-bit color. Imagine 36-bit color is 12 bits more than 24-bit color. And that is, it has 4,096 times more color than the monitors you're looking at. So these are really, really good. Really, really expensive. Okay. So that's the nature of digital color. There's more to it. We're not going to go into it. Typically, also computer graphics and everything that you're talking about. Well, hey, we've got 24 bits, but our integers can hold 32 bits. What are we going to do with those other 8 bits? We don't want to let them go to waste. There's another signal here called A for alpha. Alpha, written like that. And alpha is a concept invented by Alvy Ray Smith and Ed Catmull. Alvy Ray Smith went to Microsoft Research. Ed Catmull is the founder of Pixar, Toy Story, etc., that company. And I believe he's now the president of Disney. And also a great researcher in computer graphics. Right? So alpha, what it does is this allows you to specify a transparency or opacity of the color. And this is the basis of how you do painting in Photoshop, how you put 2 images together. Right, so alpha is the basis of combining images. Okay? All right. I have no idea where I was. Anybody know? I know I'm going to talk about bit twirling.
Yes, have you actually talked
Not really. Okay, so see, Sophia, we got onto the question that you asked, right? Yeah, okay. So it's her fault. Everybody, it's her fault. Okay. Do you have it, while we're on this subject, do you have any other questions about color?
One.
All right, I'll permit that.
So I saw a video about how there's different ways that they light the pixels. There's either like the backlit where it's the entire thing is lit at once, or each pixel lights each.
Mm-hmm.
Like there's a light for each one. If you're like the red, green, and blue, it's how you mix them is by how intense one is. Would you have to have each pixel lit by light, or is the backlit somehow like pixel only allows a certain amount of light to get through?
That's so what you said is, do you have to light all the pixels, all the colors, or is there a backlight that lights everything and then pixels limit the amount of light coming
So
through?
is it like one is giving light and one is keeping light from going through?
Well, they're all giving light. That's why you can see it at night. Right, but you're also right. Some technologies are just have a white backlight and then filter the white light coming through. That's your limiting ones. Other technologies have microscopic LEDs that are lighting their own reds, each pixel's own red, each pixel's own green, each pixel's own blue. Right? So both technologies exist. The one that has the backlight is a little less expensive. So LCD versus LED monitors. Okay. Yeah.
So what do the what is it, OLED?
Right.
Because they're the ones that you can get basically absolute black instead of
Right.
weird gray.
Right. Right.
Stuff.
Yeah. So you can't get black on a backlit display because there's a limit to how much the filters can filter. So on their maximum intensity of filtering, they're letting through as little light as they can. They're still letting through some light, and that's why you can't get a black. Now in OLED technology, which is like mysterious to me because what does the O stand for? Does anybody know?
Okay.
And there's
Organic. Like, well, what does that even mean?
I'm using organic crystals
Uh-huh.
to do something. I can't remember.
Well, I'm thinking that if you put two OLED monitors next to each other in a dark place, leave them a while, after a while you'll have three.
What? No.
They're organic, right? So, I don't know. What are they, alive? You water them? What do? What do they eat? What do they poop? So this is what keeps me up at night.
A light-emitting diode containing thin, flexible sheets of organic electroluminescent material used for visual displays.
Electroluminescent. So sort of like the algae that glows.
Perhaps.
Yeah.
I think it's a bit more sophisticated.
Yeah, who knows?
It's not. It's not.
It's not
It's not.
more sophisticated?
No.
Yeah. Well, it's cool, whatever it is. All right. One more question, that's it. One more question on color. Anybody? Yes, Kat.
With 4K monitors,
Uh-huh.
is it just, you talked about how with lower monitors, how the bits like squish together so you won't get as varying degrees of color. With the 4K, is it just having more of an ability to not smush them together?
So the smushing, we could talk about a few different types of smushing, but the smushing I was referring to with lower quality monitors is the smushing that happens in the depth. So you're seeing a reduced number of colors. You're not seeing all 16 million. You're not able to see all 16 million. So for instance, particularly at the dark, in the dark colors, the levels tend to look the same. Now the 4K refers to resolution. So HD TV. So what have you may have seen SD. Has anybody ever looked at an old-fashioned TV that's not an LCD or LED? Huh? What? Anybody? Okay. So that was SD. That was a standard definition. And that peaked out in the United States at about 720 by 486 in resolution. It turns out in different countries, the dimensions were a little bit different. In Europe, their video standard was 512 high. So their pictures looked a tiny bit better. Then we've got HD. And that has a resolution of 1920 by, I believe it's because people are usually concerned only about the horizontal. But 1920 by 1280.
Isn't it 1080?
1080?
Definitely 1080.
No.
1920 by 1080. At least in After Effects, HD is 1080.
Yeah, because it's 1080p.
Yeah, but 1080p doesn't refer to the vertical. It refers to
It's definitely
the horizontal. Okay.
Look, see, that's the
1920 by 1080.
1920.
Yeah. Well, like when I wrote this down, I was saying people concentrate more on this. All right, so let's say it's 1920 by 1080. Okay. So, all right. Okay, so 1080p versus 1080i. Okay, progressive and interlaced. We're not going to talk about that. Okay. All right. Okay. So now, what is 4K? 4K is going to be 4096 by something, and there's also 8K, which is 8192 by something.
That's a lot of pixels.
So this is 4K and 8K.
Is there any point in that much definition?
That's exactly what I was going to talk about next.
I guess.
That's exactly what I was going to talk about next. Now, the human beings have a limit to the resolution. We have a limit to how small a dot we can see. Also factor in that we're not looking at a TV like this. The TV is far away, which means the dots are, to us, we perceive them as even smaller. In fact, they all blend together. Now, at the point in which you can't distinguish an individual dot anymore, that's called the extinguishing resolution. And the extinguishing, this is far beyond. Human beings can't, on a television, nobody in the universe needs one of these. But they're going to sell them to you hard. Okay? These. Mostly nobody in the universe needs one of these.
I have one.
Okay? You paid for a marketing gimmick.
It looks better than the previous one.
Okay. Now, the only people who are broadcasting in 4K are the digital streaming services. So it's rare, not unheard of, but it's rare for a cable company or a satellite company to send out a 4K signal. But they'll tell you, you have to buy one, but you can't make use of it. All right? So the human beings extinguishing resolution is somewhere in here. And when you factor in normal viewing distances for television, forget about it. You know, this is great. This is overkill. This is sucker. Okay. Now, as it happens, the high-end motion picture capture devices are digital cameras now, not film, although film is still used quite a bit. The high-end capture devices, the cameras, are 8K. Now, for them, there's a reason, because the more pixels you have, the easier it is and more flexibility you have for outputting smaller images. Okay? So it makes sense for George Lucas to use 8K in his camera, right? But it doesn't make sense for human beings to rush out and buy an 8K television for viewing.
Are they even selling them?
Yeah,
No, that's just.
yeah.
Unless you have like a massive theater in your own house, that's completely.
Well, for ordinary people, no, there's no point at all. As a matter of fact, for ordinary people, I make the claim there's no point in having a massive theater. Okay, because after I sold my first business, I spent about 120K on a home theater. It was a theater in a home. Had stadium seating. It sat 32 people, right? And it was downstairs in the basement, so I hardly ever used it because it was too far away to walk. Okay? So you know what you're better off having than a home theater? Is really nice TV in your living room. Yeah.
Samsung's 8K TV is $15,000.
$15,000 for a 8K television that's not as good as the 8K TVs that motion picture people use. There you go, $70,000 TV. Now you wouldn't call that a TV, you'd call it a monitor. All right? Yeah. You know, I don't know about, this reminds me of something from my own personal upbringing. I don't know what advice you got from your most important person in your life when you went off to college. You know, maybe dad set you up and said, here's a lesson for life, son or daughter. Or maybe mom, maybe it was another type of trusted individual. The only advice I got was from my brother. And he said, remember, Perry, someone will always have a better stereo than you. But that's what I'm talking about, television. Right? Remember, somebody's always going to have a better TV than you.
Well, I mean, obviously, there's a ceiling. At some point, you have the best of the available options.
And then you die.
And then, you know, sure.
Right.
But you at least you had it for that.
Yeah.
Better time.
Okay. All right. So no more questions on this subject. Let's get back to bit twiddling. All right. So there are some operators that you have not used before.
What is a bit shifting? Is that what you're talking about?
Well, the generic bit shifting is one kind of bit twiddling.
Okay. Yeah.
Yeah. So I don't know if you knew this, but there's 3 levels of messing with something like a knob on a radio or volume. There's 4 levels: tweak, twiddle, fiddle, and frog.
Say that again?
Tweak, twiddle, fiddle, and frog. Sounds like a law firm.
All of those are definitely not words.
Those are definitely what?
Some of them are definitely not words.
They're not words?
Yes.
Okay, so look up frobbing and dial.
There's no way frogging is a word.
Look up the verb to frog.
Apparently, content may be.
Oh, okay. Well, it's a word then, right? Well, and there may be a non-technical, organic.
Flipping a frognicate. So the word is actually frognicate.
Okay. Okay, so tweak, twiddle, fiddle, and frog. I wanted a company named Tweak, Twiddle, Fiddle, and Frog. And I've answered the phone. This is Frog speaking. So tweaking is when you're making a very, very tiny adjustment. right? Doesn't that sound like, I'm tweaking my code, right? Twiddling is carefully making larger adjustments. Fiddling is you're just playing with the dial, just going like this. And frobbing is you're practically pulling the knob off the machine that it's attached to. Okay? So we're talking about twiddling, bit twiddling. Also a technical term, swizzling. You can swizzle your bits. Okay. So there's 4 operators that you have not used. Okay. So you think you've seen this, and indeed you have. However, operators can be overloaded, right? So you can change the definition of plus. You can change the definition of minus. So streams, stream input and output, change the definition of these 2 operators with respect to operating on a stream. So this is stream output, stream input. But if you're not working on a stream, the original meaning of these is to shift your bits left, shift your bits right. Now you've seen and. You probably haven't seen the or, this symbol, in your C code. You may have seen it. I may have typed it on screen when I was working with Linux. But you've seen and that is, oh, you have, of course. You've seen you've seen and or, right? Pipe. That's called pipe. So and pipe. So this is logical, and these are bitwise, like Samwise, only with bits. It's funny that they repeated the name Samwise, because that's Tolkien, and then it appeared in Game of Thrones, so who knows. Oh, and they're the same people. Duh, that's why they used it. Sam is to Frodo as Sam is to John. Did you ever think about that? Just occurred to me. It's very, very difficult to have a mind like mine. It's a challenge. Okay. Anybody know what I'm talking about? Anyone? Yeah. What?
I'm so confused. It makes it so much harder that I am a Sam.
Okay.
And I've seen none of those things.
Okay, so Samwise is Sam Gamgee is Frodo of the Hobbits, is a Hobbit, and he's like the caretaker, best friend, BFF for Frodo Baggins, who's the main character in The Lord of the Rings. And then in the Game of Thrones, Samwise, or Sam Tully, is the best friend, same thing as Samwise Gamgee, for Jon Snow. Okay, so who's your best friend? You don't have to answer. Okay. But okay, so Sam is to John as Sam is to Frodo as Sam is to Sophia. Now it all makes sense, right? Yeah, there you go. Okay. So these are bitwise operations, and then we're going to talk about these, and we're going to talk about those. So say 1 byte. 1 byte has 8 bits. Let's say you had that value. What value is that? 1. First of all, what radix is that in? What base is it in? 2. It's in base 2. That's binary. All you get is 1s and 0s. When I was little, sometimes we didn't have the ones, so I can't have myself.
I don't know what this means.
Yeah. It's like when I was little, I had to walk uphill to school both ways.
Okay, so it's just wrong
It's-
to make a point.
It's humor. It's humor. Try it. Okay, so this is 8 bits. It's binary. This is the ones place, and the twos place, and the fours place, and the eights, and the 16s, the 32nds, the 64ths, and the 128ths. 128ths. Just like in decimal, we have the ones place, the tens place, the hundreds place. It's exactly the same thing with a different radix. Base 2, base 10, base 10, base 2.
Right?
Right?
Got fractional bases. It's really weird.
Okay. Anybody have any questions? Okay. So, in common with base 10, base 2, it's the ones place. So what is the binary? This binary is telling you what number in base 10? The number 1. You want to see an easy way of multiplying by 2? Okay. 2 happens to look like this. What just happened? See, there's a 1 in the 2's place, so that's 2. But what is the pattern here? All we did is what? We shifted to the left. So in your code, you could conceivably multiply by 2 by saying, if this is an integer, you could say n. You could say n shifted by 1. That's a multiply by 2. And if you said n shifted over by 2, that's a multiply by 4. How about n shifted over by 7? No, that's 2 to the 7th. So 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7th. So that's a multiplier by 64. Right? Now, as it happens, if you wrote, the compiler is smart enough that if you wrote n times 4, it'll actually convert it to this behind the scenes, because computing this is faster than computing a multiply. If you had an integer and you wanted to divide by 2, what do you think you do? Shift right.
How do you do decimal places then?
What?
How does it do decimal places then?
Totally different. Totally different. And we won't cover that. Okay? All I will say about floating point values is they are separated into 2 sections. And you may have done this in high school or some other class. So there is a section that's big called the mantissa, and a section that's smaller called the exponent. So you can think of this as, in terms of hardware, this is like something times 10 to the minus 4. Right? So this is kind of like scientific notation, but that's a weak analogy. Right? That's how floating points is done.
What if you do try to shift it?
Did you have a question? Okay.
Right.
Yeah. If you shifted by a floating point number, smoke.
So the compiler wouldn't like
No, the compiler would not like it. Yeah. Yeah, I would not like it. I think that you would get a syntax error. However, if you cast the float to an end, that would work. Okay? So there are other uses for shifting as well. How about, how do you know if a number is, let's move into another one. How do you know if a number is even? What would you do? Yeah?
I would mod that too.
Mod by 2. Yep, that makes sense. So mod by 2, n mod 2 can result in either 0 or 1. Well, isn't it true that the places in the binary representation are zeros and ones? There seems to be a connection here. So you could say n and 1. And if this will produce a 0 if it's even, or it will produce a 1 if it's odd. Let's take a look at that. You're testing the low order bit. That's called the low order bit. You're testing to see if it's a 1 or a 0, because if it's a 1, it's odd. If it's a 0, it's even. But let's take a look at what it means to do a binary and. So what did I just do there? So let's say n was 15. Okay, so n equals 15. In binary, that's going to be a 1, 1, 1, 0, 0, 0, 0. And I want to know if this is even or odd. So what I wrote there is n anded bitwise and with 1. So let's draw 1. And that's going to be 0, 0, 0, 0, 0, 0, 0, 1. So the bitwise is literally, use a literal interpretation of bitwise. It's going to do this and that. Let me do it the other way. This and that, this and that, this and that. Okay, so 1 and 1 is 1. 1 and 0 is 0. 1 and 0 is 0. 1 and 0 is 0. And 0 and 0 is zeros. See? So if the result of n bitwise and 1 is non-zero, means that bit 1 was on, bit 0 was on, and that means it was off. Right? Okay. How would you know that something is a multiple of any other power of 2? You could play the same trick. So rather than doing something like mod 8, let's say you're doing rand mod 8. Now this only works with power of 2. Okay. So what is 8? The 1's place, the 2's place, the 4's place, the 8's place. Okay. Something rand mod 8, what values can that produce? 0 through 7. Mod 8, 0 through 7. Well, add up, what's 1 plus 2 plus 4? George Washington's horse? What's 1 plus 2 plus 4? 7. So you see there's a connection here. So if you anded rand and 7 is the same thing as that. Because all you're letting through are those 3 bits? So the answer is a number between 0 and 7, inclusive. So bit shifting and bit twiddling and logical instructions have huge, huge applications, especially in courses and work that involves hardware. So if you think that someday you might work with like a Raspberry Pi to control something, maybe make a small robot, an Arduino, perhaps you've heard of that, you're going to be using bit shifting and you're going to be using ands and ors. Now, as a final point, I was talking about how the bitwise operations work. What about comparing 15 or 1 versus 15 or 1, or 15 and 1 and 15 and 1? So this one we just did, right? And what was the answer? The answer was 1. But what's the answer to this one?
0.
Anybody? The answer to this one is true. This is 1. This is true. Your hint is this is logical and this is bitwise.
What does logical numeracy mean?
Well, before there was the type bool, we only had integers. So the standard is that 0 is false. Anything other than 0 is true. Do you remember printing out a bool and getting a 0 or a 1, and then you learned how to get true or false? Do you ever do that? I know that some students have. No? Some. If nobody says yes, then I'm just sad. Okay, so somebody said yes, even if you don't mean it. Yeah, okay. So if you had bool A and a bool B, if you did a C out of A and B, you'll either get a 0 or a 1. Okay? And there's something you can do in to your stream that will give you true or false. Okay? All right, it's in Zybooks and on the final. Now you go read Zybooks. Okay. So a bool, A and B, ANDed together would be true or false. If you wanted to print it, it would be a 0 or a 1. Recall that only 0 has a specific meaning. That's false. 0 is false. Anything other than 0 is true. So that's why this would be true. Because neither of these are false. Neither of these are 0. So if you had 15 and 0, that's false. Looking at the truth table, I hope that everyone has seen a truth table before. You must have when you learned about logical and logical or. So what's true and true? Yep, what's true and false? And false? And true and false again? Good. Right? Now let's look at OR, logical OR. Okay, we can do the same thing, play the same game, true and false. What's true and true? Or true or true? What's true or false? And the same here, and false or false? False, right. Now let's look at binary or bitwise and an OR. Excuse me, only one pipe. 0 and 1, 0 and 1. 0 or 0. I'm going to erase this and just reverse these so that you see the pattern more readily. Let's put the true there, kind of, so to speak. So 1 or 1. 1 or 0. 1 or 0. 0 or 0. See, it's that for only a single bit, it's exactly the same as this for the logical notion of bool. Let's do the same thing for and. So we did the truth table for logical and. Let's do the truth table for bitwise and. 1 and 0, 1 and 0. What is 1 and 1? 1. 1 and 0? And 0 and 0. So compare. Do you have a question or are you stretching? Stretching? Okay. That's fair. Now, if you were at an auction, you would have just bought the pony. Yeah. I don't know how many comedies have that where somebody's being tickled with a feather and they end up buying a Van Gogh. It's a common trope in comedy. Yeah.
So the two ands, if you do like 15 and 1 versus 15 and 1 and 1. One is just looking at maybe like logic wise, and one is looking at the numbers.
The individual bits.
But they're both going to give off a 0 or a 1. The 1 just says true or false.
Correct.
0 or 1.
Correct. Yeah, correct. Okay, now there's a few more operations. There is yes. So let's say we said not n. Now you've already learned about a not. The logical not is that's whatever value the bool has. So if this is true, this makes it false. If this is false, this makes it true. So there's also a bitwise negate. It's not really a not, it's more like a negate. So if n were 15, right, then not n or negate n would be all the bits just flipped.
What number?
Let's add it up. So this is 16s, 32s, 64s, 128s. So whatever it is.
Could you not just do 256 minus 15 and get the rest of the numbers?
What?
Like, if you have all the ones, it's 256, right? And then 4 ones, it's just 15. So if you did 256 minus 15, would you get that number?
I think so, yes.
Okay.
Right. However, not always.
I do not believe you would in this case.
Yeah.
You got one more.
Hmm?
128 minus plus 64 plus 32 plus 16 gives you 240.
Yeah, I'm just not going to do the math in front of you. Yeah, you never do math in a classroom.
Wait, math class? You do math all the time.
Yeah, well, they're flying without, they're doing a trapeze without a net. And they probably practice the same problems over and over and over again. Because think about it, how easy is it for you to make an arithmetic error on a test? It's just as easy for an instructor to make an arithmetic error on the whiteboard, but it's far more embarrassing.
No, except that the students, they have mercy. Teachers don't. If I see making the arithmetic
Oh, you have mercy for me.
yes.
Oh, you fool.
Oh.
Thank you.
A student would say, "Oh, look, we got to add this or
Yep.
something like that,"
Yep.
and then you just go on with their day.
Okay.
Teacher would be like, "Red X,
Red X.
you
Yeah.
fail,
Yeah.
no mercy."
I've shown mercy in this class, haven't
Have
I?
you lost?
Yeah.
Maybe.
Yeah. Well. Okay. So I do know that the answer to your question, Sophia, was it depends, because remember you have signed and unsigned. Because if you had 255 and it was a signed integer, it's actually a negative number. So a negative number minus a positive number is going to be an underflow. Yeah.
I added all this, and my computer is correct. That's not correct, because if you subtract 256, if you subtract 15 from 256, you get 241. And if
Yeah,
you add
I was
all
thinking
those
about
together,
there was an even and an odd there.
you get 240.
Mm-hmm. Yeah. Okay.
So you have to add one to everything?
So maybe the right answer is it depends, where it depends means never.
Yeah.
I was gonna say, I'm having the same thing. I could think
Yeah, yeah. Okay. Well, if you added all the ones together, what is 250? Wait a minute. All the ones together isn't 256. It's 255. So what's 255 minus 15? 240. Right.
So why isn't it 256?
Because the 256th bit is in the next byte. It goes 0, 1, 2, 4, 8, 16, 32. I missed one. Did I start with 0? That would be wrong. 1, 2, 4, 8, 16, 32, 64, 128. The 256s would be in the next byte. So it's 0 to 255. 255 minus 15 is 240. Okay, see, you never do arithmetic in front of a class. Yeah. Okay, so what you've learned so far is bitwise AND, bitwise OR, bitwise negate. You've also learned, that's what you've learned so far. There's one more worth talking about. And that's this. Okay? So this one is exclusive OR. Okay? Let's do a truth table for exclusive OR. Often abbreviated XOR. So 1, 0, 1, 0. Let's see. We're looking at OR. Now I'm forgetting what exclusive OR does. Let's see. I believe that exclusive OR, if I remember correctly now, if both values are the same, so this one and this one, then you get a 0. But if the values are different, you get a 1. Is that right? Thank you. Okay, so it's 1, 1, 0, 0.
They're both 0, you get a 0. If one is true, you get a 1. If both true, you get a 0.
There you go. Right. Okay. So this is also cool. It's often on technical interviews for jobs. Let me give you a common technical interview question. Okay, now challenge yourself. We have a few minutes left. So write or come up with at your table, at your seat, a function. Don't look it up because it would be no fun. Write a function that swaps A and B without using a temporary variable.
A and B being integers?
Yeah, A and B being integers. Well, A and B being anything. Yeah, anything. Because it's just bits. Okay. Well, anything. Well, okay, let's just call it unsigned bits. Okay, so ordinarily you would do it like this, right? You'd say temp equals A equals B equals temp. Correct? So we save A, move B into it, and then put the old value, the value of A, the old value of A back into B, and now A and B have been swapped. Now, do it without temp.
Can't you take A or B? Because it's swap.
Well, don't talk to me. Talk to your colleagues. Everybody talk to each other. Can you do it? Can you do it without a temporary variable? This challenge. I challenge you. I double dog dare you. Triple dog dare you. Is there anything bigger than that? Okay. Well, nobody's talking. So maybe that's a sign of capitulation, resignation. Okay. So if you execute these 3 instructions, it will actually swap the values. If I remembered it right. I think I did. Okay, let's try it with 1 bit, shall we? Okay, I think we have time. So here's A, and here's B, and how about we set A to 0 and B to 0? Is that a good idea? We want to swap them? How will you tell the difference? Right? So let's set one of them to 1 and one of them to 0. Okay, so this is A equals A exclusive OR B. So what's the result of this instruction? So this is instruction 1, instruction 2, instruction 3. Instruction 1, instruction 2, instruction 3. So they're different, right? All right? Okay, so all right. So A is different from B. So if I did it right, this is going to be that. And now I'm getting confused immediately. Because this is going to be the same and this is going to be the same. Okay, your homework is to prove that it's true. How's that? That's another teacher thing you can do. All right, we'll cover it next time. All right, we have about 7, 8 minutes. I'm assuming there are no questions about the project. You do? Okay.
So the person who's turning in, if you're doing partners who didn't actually have to code in, you don't have to turn in a new.
Please turn in, everybody turn in. Turn in a text file. Folks, if you turn in the wrong thing, there will be no second chance this time. If you turn in the workspace file, sorry, you get a 0. Okay? Yeah. Everybody turn in. So the partner who didn't do the code, turn in a text file.
I turned in a link to my kid.
Then I will give you a 0.
Yeah.
I will. I will give you a 0. Do as I ask. Yeah, you can just submit again. Yeah. Okay, everybody?
Actually, do have a question.
Yeah.
So with our credit, are we allowed to make any changes? Not changes so much as an addition to HPC.
Yeah, knock yourself out.
Okay, so then we just give you the H, because we didn't change what you had, we'll just give you ours. We added an additional to the, we added something to the stream.
Okay. Yeah, because I mean, theoretically, another way of looking at that is you created another HTTP, and just because you said you're not changing, you're just adding.
Yeah.
Yeah. So it's like adding another include file.
Okay. We just wanted to make sure it wasn't going to be like every change.
Okay.
Like again, this a low commit.
That's okay.
And they added it.
Yes, totally okay.
It's almost 100.